Hi, this is Dr. Simon Romero, and I'm here to present you the video tutorial for section 14.2, Limits and Continuity in Higher Dimensions. These are the topics, these are the practice problems, and I suggest you to do more. So the idea is to explain two theoretical concepts that are going to be very important when we deal with the equivalent of the derivative of functions of several variables, that are limits and continuity. First of all, we're going to start with the definition of open disks in the plane. This is a definition that we're going to use later on, so it's better to just introduce it right now. So the open disk center at AB with radius delta is a set of all points x, y, and R2 whose distance from AB is less than delta. This is more or less how would you write it in a set notation, and geometrically what it says is all the points that are less than delta away from AB. So you can see that it's all the green points that I'm putting over here. This definition helps us to understand the formal definition of limit. An important thing is I am not going to require you to really memorize this definition. I'm not going to require you even to understand it right away. I'm not going to ask you about it in the future. I just want you to give you an idea of what it is. If you can understand it from the idea that I give you, I am happy about it. So if you're interested to learn more about this definition, you should take a class called Real Variables. The formal definition says something like this. I'm going to just try to explain you what it says geometrically. So geometrically says that the number L is the limit of a function if this happens. If for every small distance that you give me in the range, I can find a distance in the domain such that all the points that are distance less than delta from AB go distance less than epsilon to L. So that means that I can make the values of the function as close as I want to L by just taking a sufficiently small ball around AB, and all the points in that ball will map to something closer than epsilon to L. So that's a formal definition of limit, but I'm going to move on. So we want to try to get around the limit, the formal definition of limit, because it's a little bit cumbersome and it's maybe too difficult. So we will try to do the limit laws. The limit laws are proven by using the formal definition of limit, so I am not going to prove them right now, but I'm just going to tell you what they are. So the first one is the most basic limit, that if x and y approaches to AB, then x approaches to A, and if x and y approaches to AB, then y approaches to B. The next one is constants can go outside of the limit. The limit of the sum is the sum of the limits. The limit of the product is the product of the limits. The limit of a division is the division of the limits as long as the limit of the bottom is not equal to 0. You can also use the squeeze law if you can, and notice that there is no L'Hopital for several variables. We're going to use L'Hopital when you change a limit of two variables to a limit of one variable. Let me give you an example of how you can use the limit laws. Well, first of all, notice that directly we cannot use the limit laws because the limit of the bottom is equal to 0. So we're going to try to make some algebraic manipulations in order to get something that doesn't have a denominator, or it has a denominator that is different from 0 when you take the limit. So the thing that we have is I'm going to multiply by 1, but that's not the one that I want. I'm going to multiply by this, and notice why I'm doing that, because I'm going to multiply by the conjugate of the denominator. Remember, the denominator is the thing that I want to get rid of or change it a little bit. So we end up with this. Still, this denominator gives you equal to 0, but notice that in the top you have a common factor x. When you take the common factor x on the top, on this particular top left factor, the thing that you have is you end up with a factor x minus y that cancels with x minus 1 on the bottom, and then you obtain something that doesn't have a denominator. So finally we can use our limit laws. The limit of the product is the product of the limits, and each one of these limits gives you equal to 0, so the total limit is equal to 0. The next thing that I want to show you is the non-existence of limits. So there is a way that we can prove that a limit does not exist in functions of two variables, and it's going to be more or less the same idea as when we have a single variable. So the way that we're going to do is, if you can find two ways that you can approach AB with two different curves that give you two different limits, then the limit is not going to exist. So the thing that I'm saying is, if you take AB and you approach from a curve C1 and you compute that limit, and that limit gives you a number, and then if you approach from C2 and that approaching from C2 gives you another number, and those two numbers are actually different, then the limit is not going to exist. Let me give an example of what I'm talking about when I say approach in y way along one curve and another different curve. So let me prove that this limit does not exist. The method 1 is, our objective is to find two curves that approximate 0, 0 that gives you two different limits. By curves I mean just one-dimensional objects in the plane, so they can be lines actually. And those are the ones that I'm going to use for this example. So for example, take the line y equal to 0. The points on this line are of the form x, 0. So notice that the thing that we're doing is we're replacing y equal to 0, so that will leave us only with x as the variable. So I'm replacing y's for zeros, and then I'm going to take the limit. So the top is 0, the bottom is 2x 2 times x to the 4, and then that gives you 0. The division of those two things is 0, and the limit of a constant is equal to 0. Of this constant, 0 is equal to 0. So now we're going to do a different approach. We're going to approach from the line y equal to x. You may wonder why I didn't take x equal to 0, because it's still going to give me limit 0, and remember, we're going to try to find two limits that give you different numbers. So let's try y equal to x. When you take y equal to x, all the points of this line are in the form x, x. So when you take that, the thing that you're replacing is y with x, so I replace y with x, and then notice that the thing that's going to happen is the top and the bottom are going to have the same power of the x, so the x's are going to cancel out. In this case, they cancel out. We end up with 6 over 3, and 6 over 3 is equal to 2. The limit when x approaches to 0 of 2 is equal to 2. Notice that in here, in these cases, we're replacing a limit of two variables by a limit of one variable, by just setting the other variable equal to something, by just picking the curve that approaches to 0 in a different way. This method is actually very useful and very versatile. The problem is you have to pick the right curves in order to get your answer or your proof. Notice that in this case, in 0 is different from 2, we conclude that the limit does not exist. You have to get two different limits in order to conclude that the limit does not exist. The method 2, it takes into account all the possible lines that contain the origin. So notice that it's more or less the same thing. All the lines that are approaching the origin have this particular general formula, so the points on such lines are of the form x, mx. So I'm going to do the same thing. I'm going to replace y by mx, and then since the only variable that we're going to have left is x going to 0, so x is going to go to 0. Now in here I'm going to have something like this, and then I'm going to take common factor x to the 4th, and then I can cancel the x to the 4th, so I'm going to end up with this that doesn't depend on x, so you end up with this expression. Now if I can find two m's that give you two different numbers, then I will have that the limit does not exist. And as we saw in the previous method, the line with slope 0 gives you 0. You can just plug in m equal to 0, and when you take m equal to 1, you have the line of slope 1, and that gives you equal to 2. So we can conclude that the limit does not exist. Now, another way to actually compute limits is using polar coordinates. So polar coordinates is just changing, instead of putting rectangular coordinates, you represent a point by the distance to the origin and the angle. And the one that we're going to use here is we're going to use these two formulas, but the important one actually is going to be this one. So let me tell you how it works. So evaluate this limit when xy approaches to 0 of that. Notice that we have x squared plus y squared in the top and in the bottom. So the thing that we're going to do is, using that y goes to 0, 0, we have that r goes to 0 and r squared is equal to x squared plus y squared. So notice that the thing that we're doing is we're replacing two variables by one variable. So we obtain that the limit that we need to compute is equal to replacing this by r squares. Remember that you can only do this if you replace all the x's and all the y's by r's. So you have the sine of r squared when r goes to 0 of sine of r squared over r squared. Then we'll apply L'Hopital. Notice this is a limit of one variable, so we can do that. We obtain this, and then we cancel the 2r, so you have the cosine of r squared, that gives you equal to 1, so that's the limit of this particular function. So that takes into account limits. Now, the continuity of function is a function of two variables is continuous if the limit coincides with the function. The thing that we're going to say is if two functions are continuous, then there are a lot of combinations that will create continuous functions. Multiplying by a constant it still give you a continuous function. Adding, multiplying, and dividing continuous functions is going to give you also continuous functions as long as you divide by something that is different from 0. And moreover, if you have a function of two variables that is composed by a function with a function of one variable, that will give you something that is continuous. So this will create a lot of continuous functions that are going to be helpful to talk about differentiability in functions of two or more variables. And that will be all for this video tutorial. Thank you.